This screencast is going to introduce you to probability distributions. In particular, we're going to be talking about discrete probability distributions in this screencast, but all of what I'm talking about can be easily extended to continuous probability distributions. So let's talk more generally about what is a probability distribution. It is a model that describes the probabilities associated with the possible outcomes of an experiment. And a lot of times it has to be determined experimentally, or if it's based upon probability, you can come up with theoretical models. Probability distributions are useful in engineering when we want to know something about a random variable, so perhaps we can optimize the process. For example, what proportion of batches conform to specifications? How many defective products are produced in a manufacturing process? There's also this notion, as I alluded to a few moments ago, about discrete versus continuous probability distribution functions. So it depends upon the type of random variable that is being modeled. A discrete probability distribution function, or discrete random variable, is a variable that can only take on integer values or whole number values. A couple of rules and notation. The probability distribution function, again, we refer to that as lowercase f, of a random variable capital X. Now there's a difference between capital X and lowercase x. Lowercase x in general refers to an actual number, so this might be the number 4. Capital X just refers to the random variable x that's represented by that sample space. So based upon what is known about probabilities, and you guys have seen this before, the probability distribution functions represent probabilities. So probability has to be greater than or equal to 0. It cannot be negative. And the sum of all probabilities has to be 1. So I've got an example here. We have x ranging from 1 to 5, 1, 2, 3, 4, 5, and we have the probability distribution lowercase f as shown in the lower row here. So I have a question for you. For f of x to be a probability distribution, what must f of 3 be? In order for this to be a probability distribution, the sum of all f of xi's has to equal 1. And in that case, this has to be 0.15. If we plotted this probability distribution, it would look like this. And remember, the area under the curve, that's just the summation, has to equal unity. The total probability has to equal unity. So the nice thing about probability distributions is you can always calculate a probability by just looking at the area underneath this curve. For example, the probability that x equals 3 is just equal to 0.15, that's the height of this bar, divided by the total area. And the total area for these PDFs is always going to be 1, so the probability is just 0.15. We can also calculate some other examples. What's the probability that x equals 2? Well, that's just going to be 0.25. What about the probability that x is greater than 3? So greater than 3, we would look at 4 and 5. And again, because lowercase f represents probabilities, we can just sum. So this really equals 0.15, the probability that x is going to be greater than 3. If we had included greater than or equal to 3, then we would add bar number 3 there, so it'd be 0.30. A cumulative discrete probability distribution is related to the probability distribution. It describes the probability that a random variable is less than or equal to a given value of x. Now don't get too confused here. It's actually easier than you would think based upon all this notation. The cumulative distribution function, capital F, I have in this chart, and these are in the orange bars. The cumulative is just adding up everything that's equal to or before it. So if we look at x equals 1, lowercase f of x is 0.45. The cumulative distribution function, or capital F, is just the sum of everything including that x and below. When x equals 2, capital F, or the cumulative, is just the sum of the previous 2 bars. So if you add those two up, you get that. And if we keep going, this large bar is just the sum of the previous sum and the next f of x, and so on. So it's always a running sum, and obviously if you go to the very last x, it's always going to approach 1.0 because that's the cumulative. So in fancy notation, big F of x is equal to the probability that the random variable is less than or equal to x of I. Those are the same there, so we can just sum these probabilities. So again, note the difference in notation. Probability distribution uses small f. Cumulative distribution uses capital F. Going back to our example, this 0.70 on the bottom here, we have the cumulative distribution function. That's just the sum of 1 and 2. Capital F of 3, 0.85 is just the sum of everything before it, which is also the sum of the previous cumulative distribution function plus the current little f of x. So that's how we get the cumulative distribution function. So we can answer other questions like what's the probability that x is less than or equal to 4? If it's less than or equal to 4, you can always write this as capital F of 4. All right, so I can just look up here, and that's 0.95. What if we wanted to do something a little different? What is the probability that x is greater than 2? Well, that's equal to 1 minus the probability that x is less than or equal to 2. This is capital F of 2, and we can get that from up here. So that's 0.7. 1 minus 0.7 is 0.30. And that means the probability of getting x greater than 2, meaning 3, 4, or 5, is 0.3. And that's exactly what we get up here. Let's talk real quickly about how you can characterize distributions. We have two distributions here. We have this dark blue one and this red one. And there are some differences that you see. One is that the central tendency, or the average of the blue one, is a little bit lower than the red one. Another thing you observe is that the spread in the data, or how far most of the data is from the center, is a little bit different. It's bigger for this red distribution. So we see there's a different center value and the spread. We can describe these distributions with two important characteristics. The first one is the mean. The mean is just a weighted average of each of the x values multiplied by its probability density. And we'll go through an example here in a minute. Variance is how far each x value is from the mean. We square that, and then we multiply by the probability distribution. So let's take a look at this. What's the mean of f of x? All we're going to do is we're going to take each of our x values and multiply by each of our f of x, the corresponding f of x, and then we're going to sum that. So writing that out, we get the following, and if you plug that into your calculator, you get a mean of about 2.05. If we go back and take a look at our distribution, what this means is at 2.05, we have half of it to the left and half of it to the right. Let's look at the variance. The variance is given by this formula. I'm going to write this out for each of the x values that we have. So we write that out, all the terms there. When we put this into our calculator, we end up with that the variance is 1.45. Variance and mean are just parameters that you can calculate from these formulas. And if you want standard deviation or sigma, that's just the square root of the variance, and that ends up being about 1.20. So hopefully this screencast gives you a much better idea of what probability distributions are. Thanks for watching.